Welcome, everyone. We're going to have this is a kind of an oxymoron. It's a 20-minute session that's a deep dive. So this is a hat trick to pull off. But I'm going to talk for just a couple seconds about vector search, and then I'm going to pass it off to Boya, who's a senior systems developer, that has developed our approximate nearest neighbor index that makes vector search really fast now, and she'll go into that in some detail. And Yuan Huang, who has actually used it in a project, and she's going to talk about how she did that and what the benefits are for her. So, real quick, I'll talk about vector search. Boya is going to talk about the hierarchical network small worlds, that's HNSW, approximate nearest neighbor index, makes it fast, makes it integrated with the rest of vector search, and Yuan's going to talk about her RAG app in a day. All right, so really the way vector search, what it is it's a new search operator within our SQL engine. Okay, but it's a special search that allows you to do this kind of workflow, this retrieval-augmented generation, which gives your large language models up-to-date, fresh, and private information in a very convenient way. And it all so there's kind of two steps to it. The first step is to get your vectors into a database. What are vectors? They're the output of these, smaller language models. They're built the same way as the large, frontier models, but they're specialized to just output a dense vector of many dimensions, either 384, 768, they can be 5,000 elements long, but that's a special space that is representing the meaning of words or images or a combination of them. However the model was trained, it can understand the data in that huge dimensional space. And when you have that kind of index, or that understanding over all of your data there on the right-hand side, you can take a new query, run it through that same language model, get a vector for the query, and now you're searching in your database. It's a nearest neighbor search. It's a geometric search. It's very simple. You just look for things that are close in space. So that makes it very fast, but since that dimension, that embedding, has the understanding of language, it actually works really well for natural language queries, because you take that entire question and get one vector, and it's got the meaning within that one vector, and so you can get really fine-grained kinds of searches. So that's the power, and we've put this into our SQL engine and just built it inside of everything else that we do, which makes it composable with everything else you want to do in SQL. This is just an eye chart that just shows some of the syntax, and it's very similar to creating tables and indexes. There's just new data types, the embedding data type, which actually incorporates that whole process of taking your raw data, calling the embedding model, and keeping it up to date. So anytime you put in new data with an embedding data type, it's going to actually call that embedding model anytime that happens, any new data comes in, and that makes it very easy to keep your search results very fresh. So that's just a little bit of the syntax there, but then when you actually want to use it, you can compose very complicated kinds of queries. Again, the power of IRIS, the composability. Here you've got 3 different types of searches, all within SQL. You can have your vector.product you see on the left. That's the IRIS vector search component that's doing that nearest neighbor search, that particular geometric query. In the middle, what you can do with globals and the way that IRIS works, you can make a graph representation of your data. That's very useful for some particularly complicated queries. And then on the right, you see our iFind index. That's keyword search. That's also very important for particular types of queries. Depending on what your question is, depending on what your data is, depending on what you need to do with your application. You might have a different mix of those strategies, use just one of them, and they all come together down at the bottom. That's a reciprocal rank function, is the idea that is just a different way to kind of combine those in a mathematical way. So we built vector search natively within IRIS, leveraging SIMD operations, so it's very fast, and Boya is going to talk about a lot of the speed and how that's built. You can use it from Python or JavaScript using LangChain, llama index adapters. We have that embeddings generation, so that makes it easy to keep your data up to date. Hybrid search, all embedded, all integrated and natural within IRIS-SQL. And the approximate nearest neighbor index that is very fast. So there's definitely also something coming within that embeddings data type that I talked about that does the automatic embedding. We're going to have chunking support. So that's a function that you need when you have a very large amount of text. You need to just split it up into smaller pieces and then have a vector for each of those pieces. So we're going to have that integrated and automatic. And this just gives an indication of like this approximate nearest neighbor index that Boya is going to talk about. The speed that it's brought is just actually really makes applications really feasible for billions of vectors even. So bring your hardest use cases and we'd like to talk about it. All right, with that, I'm going to hand it off to Boya.
Yeah, thanks, Tom. All right, I'm going to do a technical deep dive on how did we integrate fast vector search in SQL. I'm Boya Song, and I'm in the data models team in data platform. So I'm just going to do a quick summary of what Tom just said about what is vector search and why is it important. So vector search represents data items by numerical vectors where the semantic similarity corresponds to the distances in the vector space. And doing so enable us to indexing and querying over this numerical representation of the content. So what it means is that, imagine that you have different type of media and you want to be able to index and query them. So what you can do is that you can pick a nice embedding function where the vector representation of this data item kind of have a meaning in the vector space as well in terms of the distance. So once you pick this embedding function, when you want to query this data item, what you can do is that you can use the same embedding function to transform the query into another vector representation. So we call the vectors on the left the data vectors and the one vector on the right from the query vector. So now what we need to do is to just run the nearest neighbor algorithm to find among the data vectors the ones that are closest to your query vector, and that will be the result of this search. So here the nearest neighbor search is really a key component of this whole process, and now we're going to dive in more on this. The goal of the nearest neighbor search is to find the closest vector to a given query vector, and there are two ways to do it. The more naive way or the more intuitive way is to do it exactly. So what you do is that you just need to compute the distance between the query vector and all the data vectors and pick the closest one. So this gives you the exact solution, but it is slow. And that's why people have developed and used approximate nearest neighbor search. So the goal for an ANN algorithm is to quickly find an approximate solution to the nearest neighbor search by building data structures that can help reducing the search space. And in particular, we implemented the theoretical navigable small world algorithm. So this is a graph-based approximate nearest neighbor search that's used in many vector database. At the core of it, it uses a very simple idea. So for example, here I am standing close to Ewan, and Ewan is sitting close to Dom. So now, intuitively, one can assume that Tom is sitting relatively close to me. So that really is the base idea behind this complicated algorithm. So now the general steps of this algorithm is that we will first build a multi-layer graph on the data vectors with theoretical layers. And what that means is that the points at the higher levels are going to be included in the points on the lower level, but they can travel kind of long distance quickly. Later on, we're going to have a demonstration about like what it means. So on each layer, every data vector is connected to other data vectors that are nearby. So that's kind of the idea of like a neighbor of my neighbor should be relatively close to me. And now, given a query vector, we can travel through this graph to quickly identify a subset of the data vectors that the algorithms think are likely to be close to the query vector and only search among those points. So here's an example with a theoretical neighborhood small world graph with 3 layers. One thing I want to point out is that these layers are theoretical, meaning that all the points, all the yellow data points on layer 2 are present on layer 1, and like all the data vectors, the yellow points on layer 1 are present on layer 0. And so here, given a query vector, which is the gray dot here, gray/black dot here, the search begins at a random point on the top layer, layer 2, and it will go and find the nearest neighbor point for this query point on layer 2. And then it will go down to layer 1, where it's like a more dense representation of the data vectors than layer 2, but it is a sparser representation of the data vectors than layer 1. Than layer 0. So anyway, we went to this intermediate density layer 1, and then do the same thing that we will find the nearest neighbor to the gray point on this layer. And then finally, we go to layer 0 that contains all the data vectors, and then do the same thing to find the closest neighbors to this black point on layer 0. So that's really the most technical part of this talk. So now I'm going to talk about how we add this like within IRIS. So we added this index as a special functional index that can be recognized by our SQL compiler, and how a user can use it is through the following interface. So if you want to define this index, you can either do it in the class. Using syntax looking like this, with some parameters you can verify, or you can do it in SQL. Just use the create index query. And now, when you want to do data manipulation, which means insert, update, delete, like the SQL part, the SQL compiler will just take care of it for you, and the core algorithm on the HNSW side is implemented as described in the original paper. And one thing I want to highlight is that our implementation supports parallelized insert, and we also support true delete for people who are wondering. And for data querying, again, like the SQL compiler really handles most of the work, and the core algorithm part is again implemented was implemented as described in the original paper. And one thing I really want to highlight is that if you have a hybrid search query, which means that you want to do a nearest neighbor search with some additional conditions, the SQL compiler can make smart decisions on whether or not we should use this in an index. And I'm going to kind of talk more, give an example about this later. So now I want to just show you some of the numbers we got. So my example is really a very simple table with one vector property here. So this could also be an embedding property, but just for now, I just make it vector so that it's easier to show on this slide. And then after doing that, I inserted like 100,000 rows into this table with randomly generated vectors. And so here's some comparison between using this index versus not using this index. So on the left, I have a query that says, find the top 10 neighbor of a point I'm going to give you using the cosine distance, and do not use any index. So basically, the left column, it will be the exact nearest neighbor search, because it's not going to use any index. On the right, I have the same query, but without the ignore index hint. So on the right, for this query, our optimizer is going to pick to use the NN index I defined on the previous slide. So the average runtime is quite faster if you use the NN index. And if you look at the global reference, you can see that by using the NN index, we successfully kind of avoided reading a big chunk of data that the NN index thinks that is not necessary to read. So those are the vectors that the algorithm thinks are very likely to be very far away from my query vector. The average accuracy is 100% for the exact search, and it is 93% for the NN search. And on this, I actually want to show you an example result where the NN index didn't get it 100% correctly. So on the left, you have the results from the exact nearest neighbor search. And you can see that on the right, this result returned by the approximate nearest neighbor index is showing you a vector that has distance around 0.63 instead of distance 0.68. So one thing I want to highlight about this, besides the fact that it gets all the other 9 vectors right, is that this may or may not be a problem for your search, because these distances are really abstract concepts about how close these data items are, like either semantically or using kind of because based on the reason why you pick those embedding functions. So this 0.05 distance difference may or may not cause a big problem if you look back at the original data item for your search. And if you want higher accuracy, there are parameters you can vary when you define this HNSW index to try to make this search more accurate, and that is on the cost of maybe a longer index build time or a longer search time. So the last thing I want to talk about is to go back to the point that our query optimizer can make very smart decisions on whether to use the HNSW index in a hybrid search query. And this only happens when the runtime plan choice query optimization is turned on. I'm going to show you this comparison. There's a lot on this table, so I'm going to walk you through this. So on the left column, I have a query that says, give me the top 10 nearest neighbor to a query vector where I have an additional constraint that I want ID to be smaller than 100. So I want to remind you that my table size was actually 100,000. So ID smaller than 100 is a very, very constraining condition here. On the right, I have the same top 10 nearest neighbor search, but here my actual condition is ID larger than 0. By the way I construct my table, every row in that table satisfies this where condition. So basically on the right, the actual where condition is very non-constraining. And you can see that when the runtime plan choice query optimization is turned on, our optimizer is able to estimate kind of how constraining this actual where condition is and chose different plan based on that estimation. So on the left, the optimizer chooses to not use the NN index and go for kind of the exact nearest neighbor search. And on the right, the optimizer pick to use the ANN search first, and then among those results, test the larger than condition on ID. And another thing I want to highlight is that if here I'm not saying where ID larger than 0, I'm saying maybe where ID larger than 100, you will still get the top 10 neighbor as long as we have, very likely you're going to get the top 10, you're still going to get 10 rows back. So we have built-in code in the generated code to kind of keep fetching results from the nearest neighbor search when the query asks for it. So long story short, here I just want to highlight that our query optimizer can make your hybrid search query, our optimizer can make you have less burden when you want to use a hybrid search query. So you don't necessarily have to know how the HNSW index work. You can just give it a try when the runtime plan choice query optimization is on, and hopefully the optimizer will pick the right plan for you. So now I'm going to pass the mic to Ewan to talk about how she used everything to build a knowledge graph search in a day.
Hi everyone. I know it's eating up a little bit into your break time, but I promise it will be very easy on your mind. So I'm Ewan, and I'm a developer at the data models team, and I developed the backend code for vectors, vector as a SQL type and the vector similarity functions. But today I'm going to show you how easy it is for us to use all these functions that Boya and Tom talk about to build a knowledge graph search in a day. So just a very quick background on knowledge graph search. So it's a way to retrieve semantic information by understanding entities and their relationship. It's very easy to understand by an example. If we have InterSystems IRIS, and the relation will be offers, and then vector search will be another entity. And so this search enables context-aware search suggestions and can power voice assistant search engines and recommendation systems. So, and me and Dimitri and Elijah, we built this knowledge graph search product in InterSystems internal hackathon, and it's a solution that based on the unified data storage in Iris, and it can from 0 to a Docker application containing Iris that supports knowledge graph search in a day. And this is a complex flowchart, and all I want from it is that I don't want to read that, but the thing is that we can use Python packages, open source Python packages, and then you can use object script in Iris to reach our end result. And then you can use Python for the RAG part as well. And this is the whole code for the query function. And then the highlight is that we have two vectors to convert embeddings to vectors, and then they're also ordered by vector similarity so that you can use the fast search that Boya was talking about. So, and then we can query our chatbot questions, and then it will give a summary. And then really, the takeaway is that it's really easy to use, and you can build a product really fast. Yeah, try vector search today.